Okay, so a lot of these shapes, so this table, and there's a second table that we're going to be looking at as well. A lot of these shapes I've already mentioned, so they're being repeated, but some of them will be new, okay? So there's two different things I want to point out to you. Okay, so we have what's known as the molecular shape geometry or molecular geometry, which is the main name. Okay, so for example, linear. In brackets, okay, so in brackets is what is called the electron pair arrangement, or also known as electron geometry. Okay, so we have molecular geometry, which is the term that's written, and in brackets we have something known as the electron geometry. So when you are reporting to me the VSEPR shape of that structure, you are always giving me the molecular geometry. Okay, so electron geometry, kind of the easiest way I can explain it is kind of like how many electron groups are around a central atom. It doesn't designate if it is a lone pair or a bonding atom. Okay, whereas molecular geometry tells us and distinguishes the shape based on if you have lone pairs or bonding elements. Okay, so electron geometry is really not really a great indicator of shape because the shape changes if you have lone pairs, right? So you do not need to know, and sometimes they're the same thing because there are no lone pairs. That's why. So you do not need to know the electron geometry. Actually, I never want that reported to me. Anytime you're asked to indicate the shape, it is the shape in taking into consideration the number of lone pairs. Okay, so here we have that general formula again. So number of bonding elements, number of lone pairs on the central atom. It's always in reference to the central atom. And then there is, of course, the name, an example of the shape with real, an example using the general formula terms, and then a real example. Okay, so some of these we've already seen. So AX2, right, 2 elements and a lone pair is linear. 3 with no lone pair, trigonal planar. 4 with no lone pair is tetrahedral. Okay, now 3 with 1 lone pair, right, actually there should be a lone pair on this A, is now trigonal pyramidal. 2 with 2 lone pairs is like our water, so there actually should be electrons around the central atom. There is V-shaped or angular or bent, same thing. If you have one element that's actually just bonded in a straight line, so this could be, so this could be something like HCl, right, where you have just hydrogen, okay, that's not going, hydrogen and chlorine. So it's just a linear line. I'm hoping this makes sense to you. You just have 2 elements together. So that's the only shape it can really take on if you have only 2 things. Okay? So next we have, so again, we're ignoring the electron pair arrangement. We care about the actual VSEPR shape, considering our lone pairs. So then we have, sometimes the terms will be repeated because the shape is very similar, or the bond angles, I should mention. So this is a new one for us. So 2 bonding elements with 1 lone pair of electrons. So it's not, water is an example where you have 2 lone pairs. This is where you have only 1. However, the shape is still the same. Okay, still takes on that V shape or angular or bent. So you may have 1 or 2 that will overlap. You'll see that again when we look at linear. Okay, so trigonal bipyramidal, we already looked at in that first groupings. So you have 5 and no lone pair. So this is a new one. So it's called Seesaw. So what this is when you have 4 bonding elements and 1 lone pair of electrons. So what ends up happening is the lone pair kind of pushes the other elements that are on the same plane together. But regardless, so you don't need to know with the bond angles or anything like that. But you should know that if you have 4 and 1 lone pair, that it is Seesaw. Okay, so then we have another new one, T-shaped. This is where you have 3 bonding elements with 2 lone pairs on the central atom. So it's called a T-shape. I guess it's like a sideways T. I don't think of it that way. So here's another repeat of linear. So linear, the one we had before that was linear was 2 with no lone pairs. But now if we have 2 with 3 sets of lone pairs, it also takes on. So remember, we're ignoring our electron pair arrangement. So it's linear. The reason why is because the lone pairs, the 3 sets, actually all lie on the same plane. So these are all kind of repelling each other around here. So the 2 bonding elements kind of lie above and below that plane. Okay, but again, you really just need to remember what the shape is. Okay, octahedral was in that first set. So 6 elements with no lone pairs. Here's another new one. Oh yeah, there's a mistake here. I have a comment for myself. So there's not 25 fluorines on this. Excuse me. There's 5. Okay. So here we have 5 bonding elements and 1 lone pair of electron. That is a square pyramidal. And sorry about my sneeze. Okay. And then we have square planar. So square planar is where you have 4 bonding elements and 2 lone pairs of electrons around the central atom. Okay, so a question I get is, well, what happens if there's more than one central atom? And that's going to come up a lot in our next unit. You'll see it in the worksheets and stuff you're going to work on here today too. So let's look at something with more than one central atom for a second. Okay, so in this case, we have 2 central atoms, right? So we have carbon. So let's do them maybe different colors. So I have red carbon. So red carbon has a hydrogen, a hydrogen, a hydrogen, and a carbon bonded to it. Okay, so red carbon is like central atom number 1. Okay, so green carbon, central atom number 2, has an oxygen, a hydrogen, and a carbon. So there are 3 elements bonded to it. So you can have central atoms that are in one big molecule that can take on different shapes. Not every part of your molecule will have the same shape necessarily. So let's look at this green carbon. There are 1, 2, 3 elements bonded to it. So we have 3 elements and no lone pairs. So remember, the double bond is considered to be the same as just one bond here, because you're really counting the number of elements that are bonded, right? So this would be like AX3, no electrons. So this is going to be trigonal planar. Okay, trigonal planar. Carbon number 1, our red carbon, has 1, 2, 3, 4 bonding elements and no lone pairs, which is going to be AX4. So actually carbon number 1 is a tetrahedral shape. Okay, so the shape along the way can change, right? Yeah, that's pretty straightforward. So let's say we had a carbon, oxygen, okay, something like this. So now carbon is a central atom, and so is oxygen because it has extra electrons bonded to it on the other side. So carbon has 1, 2, 3, 4. So that's tetrahedral again. And oxygen has 2 bonding elements and 2 lone pairs. So that's like AX2E2, which is bent. So anytime you have a molecule that has more than one central atom, you must report the shape around each central atom. Okay, so I put a link to this in your on D2L, but there is a really cool simulator. Let's see if I can get this in here. Okay, yeah, so this is a really cool simulator. Let me remove everything. So I put a link to this on our D2L page for you to use while you're working on some of your homework as well. But you have a central atom here, And what you can do is you can kind of drag and drop in elements. So what it will do is you can check off what you'd like to see. They have the molecular geometry, which is the one we want, and the electron pair geometry. So if you'd like to, if it gets too confusing, just check this off. And then you can kind of drag and drop more elements, and it will, let's remove one of those. So notice it's linear, and I love how it actually shows you how these shift around. And it's nice because you can drag and take a look at it, I guess as best, this is as close as you can get to like doing it in 3D, like right in front of you with building model kits. So as you drag them in, right, you can see the shape change, which is really cool. So actually, I'll go back to this. So check this out. This is trigonal planar. Look at what happens when I add in a lone pair. Did you see how those three, instead of being equal on the same plane, they kind of got pushed down, right? Let's look what happens when I add in another one. So here's our T-shape, right? So those two lone pairs of electrons are taking up space and pushing the other elements out of the way as much as possible, right? So it'll change according to how many you add. So let's take a look at what happens if we add another one, right? So here's our seesaw, right? Here's our square planar. So it's pretty cool. I actually really like this. And then there is real, so this is just with like AX stuff, right? With just like no elements. But then you can look at real molecules as well. So here's our little water. It's so cute, right? So you can look at, sorry, right? So here is our methane, right? You can even ask it to show the bond angles. This is awesome, right? So here's our tetrahedral with the 109.5. So this is great. Like play around with this and see what you think. But it's very cool. So you can look at it with the real. So they're displaying which ones are the different elements, right? And of course, we should probably look at that, right? Very cool. So anyways, give this a shot. Like play around with it. It's nice to actually look and manipulate different things as you're working. I find it's very helpful. Okay. So this is a PH or ET or a FET simulator if you've done one of those before, but I'll have the link for you on D2L.